Dense wavelength division multiplexing, DWDM, is a technology that allows multiple information streams to be transmitted simultaneously over a single fiber. This provides a cost-effective method to increase the capacity of existing networks without the need to add additional fiber. First, let's take a look at the transmitter where we generate 32 channels. If we take a look inside, we can see that the wavelength is set to 1555 nanometers, the frequency spacing to 100 GHz, and the input power to -10 dBm. Going over to the coding tab, we can see that the modulation format is RZ. Now we jump to our optical link module, where we see the number of loops is set to 5. This indicates that we will propagate over 5 spans consisting of single-mode fiber, gain-compensating EDFAs, and dispersion-compensating fiber. If we look closely at our single-mode fiber, we can see that the length of the fiber is 50 km and the attenuation is 0.2 dB per kilometer. The dispersion parameters are set for standard specifications of a single-mode fiber. Initially, we will not simulate nonlinear effects, which is why it's currently disabled. Now looking at our DCF, we see the length is set to 10 km and the attenuation to 0.5 dB per kilometer. The DCF parameters have been set to completely compensate for the dispersion incurred by the 50 km of single-mode fiber at center wavelength. The receiver is a 32-channel WDM demultiplexer with an optical receiver and BER tester. In the demultiplexer, we use a frequency spacing of 100 GHz. Our receiver is comprised of a PIN photodetector and a low-pass filter. Here we will look at 5 of the 32 channels, channel 1, 8, 16, 24, and 32. Now let's run this simulation by clicking Calculate. Once the simulation has finished, we can take a look at the Optical Time Domain Visualizer, where we can see the RZ optical signal. We can also take a look at the OSA to analyze the multiplexed optical signal, or the WDM analyzer, where we can view the characteristics of each channel, such as frequency, signal power, and optical signal-to-noise ratio. Let's now jump to the optical spectrum analyzer after 300 km of signal propagation. And finally, we can see the eye diagram for the 16th, 8th, and 1st channel. Let's go back to the transmitter. Go to the coding tab, switch to NRZ modulation, and rerun the simulation. Here we see the corresponding eye diagrams. Let's now compare to the eye diagrams from RZ modulation. Now we're going to go back into our single-mode fiber and go to the nonlinear tab. Here we'll select self-phase modulation to activate the nonlinearities in the fiber models. This will also enable cross-phase modulation and 4-wave mixing. We'll now repeat the same procedure for the DCF. Now let's run the simulation. Looking at the OSA, you can see the 4-wave mixing products generated on the far sides of the spectrum. This is our resulting eye diagram for the 16th channel. Apart from RZ and NRZ, you can use different modulation formats such as CSRZ or duo binary. Let's first take a look at the modulation setup for CSRZ. When analyzing the optical spectrum after modulation, we can see that the optical carrier has been suppressed. Now we're going to look at a duo binary modulation schematic. When viewing the optical spectrum, we do not see the tones as we did with the other modulation formats. In summary, OptiSystem provides a user-friendly environment to analyze and optimize the design parameters of DWDM systems, such as modulation format, propagation length, channel spacing, and fiber impairments.